Okay, so we have another problem here. So the question is consider the type of 7 system shown. Matrices A, B, and C in figure question 3, 2.3 are given by, okay, so we're given the matrices matrix A, matrix B, and matrix C. And then the question says determine the feedback gain constant K1, K2, and K3 such that the closed loop pores are located at it. So the first pore, okay, so I have the conjugate of pores, of course. So pore number 1 and pore number 2 are given by that conjugate pair. And then the third pore is at a negative 10. Okay, so I want to find the gain matrix, okay, K. Okay, so K is a gain constant matrix, and it's given by this is the order of matrix K. So K is simply 1 by n matrix, okay, is 1 by n matrix. Okay, so if you look at this, the matrix is a 3 by 3 matrix, so our n is equal to 3, isn't it? So meaning that our value of K will be, the matrix K will be 1 by 3 matrix, right? So we have 3 values of K, so this will be K1, K2, K3. Okay, now to solve this problem, there are 3 methods that you can use. So the first method is the direct substitution method. The second method is called Ackermann's formula, and then the last method is okay, I'm going to explain that method also. It's somehow a bit not really complicated though. Yeah, but I'm going to explain that. Okay. All right. So let's in this video, we're going to look at the direct substitution method, and then the other video I'm going to use the Ackermann's formula, and then the other one also I'm going to use the other formula, the third formula, which I'm just okay. So let us start um, with the direct substitution method. So when you want to use direct substitution method, you have to find the characteristic equation of what? This a matrix. Okay, so get the characteristic equation of this matrix and equate to the what? To the characteristic equation of the desired pose. Okay, so the pose that you want, the desired pose are located at what? Those values, isn't it? So this can be written as what? S mu1 times the 3 poses, isn't it? And then S minus mu2, and then S minus mu3. So this equation you need to remember always, okay? So mu1, mu2, and mu3 are those poses given, right? So let's say our mu1 is equal to negative 2 plus J4, and then our mu2 is equal to negative 2 minus J4, okay? Since there are two poses there, and then our mu3, okay, is equal to negative 10. Okay, so we need to find that equation. So first let's find that equation. So S minus mu1, what is mu1? That's negative 2, so this becomes plus 2 minus, since I'm subtracting, so this becomes a minus J4. Okay, and then S minus mu2, that's plus 2, and then plus J4, and then S plus 3, okay, sorry, plus 10. Okay, so let us expand this so that we can get the characteristic equation of this. Okay, so I'll multiply one by one. Okay, okay, S by S, that is S squared, and then plus S by 2, that is 2S, and then S by J4, that is positive J4S. Okay, and then 2 by S, that is 2S. Okay, and then 2 by 2, that is 4, and then 2 by J4, that's J8. And then negative J4 times S, that's negative J4S. Negative J4 times 2, that is negative J8. And then negative J times J4 times J4. So J times J, remember, is negative 1, and this negative become positive, right? So 4 by 4, that is positive 16, okay? And then S plus 10. Okay, so here of s squared, 2s plus 2s, okay, that is 4s. And then j4 and negative j4 cancel out, j8 and negative j8 cancel out. We have 4 plus 16, that is 20. And then multiply by s plus 10. So s times s squared, that is s cubed, plus s squared times 10, that is 10s squared. And then 4s times s, that is 4s squared. 4s times 10, that is 40s, plus 20 times s, that is 20s. Okay, 20 times 10, that is 200. Okay, and then we have s cubed plus, that is 14s squared. No. Yes, 14s squared plus 40 by 20. That is where did 40 come from? Okay, that is 60s, and then plus 200. Okay, so this is what we have, the expansion of this characteristic equation. Now let us find the equation to the left here. Okay, si minus a. Okay, so si minus a plus bk. Okay, remember that k is simply equal to what? 1 by 3 matrix, k1, k2, k3. Okay, so s times I. What is I? I is identity matrix for A, which is a 3 by 3 identity matrix. So it has ones in the major diagonal. Okay, and then minus A. What is our A matrix? So our A matrix is given there as a 0, 1, 0, and then 0, 0, 1. Okay, 0, 1, 0, 0, 0, 1. And then we have 0, negative 5, negative 6. Okay, and then plus b times k. Okay, what is b times k? So b matrix. So what is our b matrix? So this is our b matrix, 0, 0, 1, and then times k. And then our k matrix is what? K1, K2, K3. So what we need to do is find the characteristic equation of this. Okay, so first let's simplify this. So s times that is s 0, 0, 0, s 0, 0, 0, s minus 0, 1, 0, 0, 0, 1, 0, negative 5, negative 6. Okay, what's the product of that? Okay, so remember it's row by column. So it will be 0 times k, that is 0. Okay, so this guy multiply by all those values, right? Okay, so be 0, 0, and then you come to this 0, 0 by that, 0 by that, 0 by that, against 0, 0, 0, and then 1 by the k1, k2, k3, that is k1, k2, k3. Okay, so we have a 3 by 3 matrix, isn't it? Why do we have 3 by 3 matrix? Because this is what? A 3 by 1, and then this is what? 1 by 3, isn't it? So this number here, rows, and then columns there, gives you the order of the resultant matrix. Okay, now let us simplify this. So we subtract, right, and do addition. S minus 0 plus 0. Okay, so adjacent elements, right? S minus 0 plus 0, that is S. And then 0 minus 1 plus 0, that is minus 1. Okay, and then 0 minus 0 plus 0, that is 0. And then 0 minus 0 plus 0, that is 0 here. S minus 0 plus 0, that is 0. That is A, sorry. And then 0 minus 1 plus 0, that is negative 1. And then 0 minus 0 plus k1, that is k1. 0 minus negative 5 plus k2, that is 5 plus k2. And then s minus negative 6 plus k3, that is s plus 6 plus k3. Now we have to find the determinant of this. So the determinant of this is equal to the characteristic equation that we need to get, okay? So let us get the characteristic equation by finding the determinant of this. So remember, when finding the determinant, this number multiplied by positive, this negative by positive here, right? Okay, so we're going to have s multiplied by what? The cofactor, right? The matrix here. Okay, where so it cancels out this row and the column there. You find the determinant of this, that is it. S multiplied by what? S plus 6 plus k3, and then minus this multiplied by that. So because we're negative, it will be plus, isn't it? Plus 5 plus k2. Okay, so this is what we have. And then if we try to cover negative 1 there, okay, so this negative and this negative, all there's negative where this negative, this number is negative, so it becomes positive, positive 1. And then we cover this column and that row. So let's find the determinant of that. It is 0 multiplied by that, that is 0, minus negative 1 multiplied by k1, that is positive k1, isn't it? So this is just be positive k1 here. Okay, and then lastly, the last column here, this element to be 0 multiplied by the determinant of what you get from here, just be 0. So that one won't even bother us. Okay, this plus k1. So let us simplify this. This is s, this is s squared plus, so this I'm going to write this as what? 6 plus k3 multiplied by s. Okay, I've just combined these guys, right? Okay, and then plus 5 plus k2, right? Like this, right? Okay, so this I've just combined multiplied by s together. Okay, and then plus k1 outside here, and then distribute that s of s cubed plus 6 plus k3 multiplied by s squared plus 5 plus k2 multiplied by s, okay, and then plus k1 outside, okay. And then you have to equate this to the characteristic equation to found for the desired pose, right? So this s cubed plus 14s squared plus what? Plus 60s plus 200. Okay, now just compare, okay? So the coefficient of s squared and the coefficient of s squared this side, compare them, right? So 6 plus k3 is equal to 14. So if you solve for k3 here, k3 will be equal to 14 minus 6, that is equal to what? 8, okay? So that's k3. And then 5 plus k2 equal to what? The coefficient of what? S there, which is what? 60, right? So from this, our k2 is equal to 60 minus 5. So our k2 is equal to 55. And then if our k3 to be, you see that our k3 will be, oh sorry, k1. Our k1 will be equal to 200, isn't it? Just direct comparison there, isn't it? K1 is equal to 200. So these are the values of the k's. So the matrix k can be written as 200, okay, 55, and 60 there. Oh sorry, 8. Okay, hope that is clear, and thank you so much for your time. So in the next video, I'm going to use what's this, Ackermann's formula, okay, to solve the same problem. We see if we're going to get the same values, okay. I'm going to use the Ackermann's formula in the next video. Okay, so we end here. Okay.